Okay, today we want to change gears a little bit and talk about combining waves together. So the first term I'd like you to write down is this term. It's called superposition. Superposition refers to the phenomena where two waves are occupying the same place at the same time. Waves are not like particles. You can have two waves in the same place at the same time. Not only that, they can move right through each other. So if you watch these water waves, you can see the waves passing right through each other, and there's moments where they are superimposing. This is called superposition. Two waves in the same place at the same time. We can see this idea of waves moving through each other when we look at the reflection of the slinky waves. You can see one wave moving to the right, but you could also see the reflection moving to the left, and you can see them passing right through each other. Okay, when you combine your waves together, you're going to get a total wave that is different than the original waves. So you can see in this example, we have a program that has three waves, a red one, a blue one, and a green one, and then the black sine curve represents the combination of the three waves as they superimpose on top of each other. You'll notice with this one that just because we have three waves doesn't mean that our combined wave is going to be bigger than our individual waves. You can see it's smaller than the biggest individual waves by a teeny little bit. Okay? So we have two different ways that these waves can interact. This is an example of destructive interference. Now it's only partial destructive interference because you can see that we still have a wave, it's just not as large as one of the original waves. So somehow the other two waves are helping to lower its amplitude. We can see this even more clearly if we just have two waves, in this case red and blue. Again, black is the combined wave, and you can see that the black wave has less amplitude than the blue wave. And that's because the red wave is out of sync with the blue wave. So as the blue wave is trying to pull up, the red wave is pulling down and canceling out part of that blue wave. So this again would be partial destructive interference. What's neat is if we make the two waves, the red and the blue, the same amplitude and keep them 180 degrees out of phase with each other, we can create what's known as total 100% destructive interference. And in that case, we have two waves in the same place at the same time producing nothing. So this is two sound waves or two light waves that are in the same place at the same time producing complete silence if we're talking sound, or producing darkness if we're talking about light. This is employed in many of your headphones. If you have noise canceling headphones, you will have a microphone that picks up the ambient external noise. It will then electronically generate another wave of sound that has the exact same properties except it's inverted by 180 degrees. And the combination of two sounds produces silence. And that way you can hear the music that is also being generated clear as day because all the background noise has been destroyed. Okay, so we use sound to counteract sound to produce silence. This is 100% destructive interference. Contrast that with this, which is constructive interference, and you can see that we are getting a wave that is bigger than our biggest wave. We're going to adjust things, and you can see if I make either wave bigger, the total wave becomes bigger too. This is happening because our waves are synchronized. The red and blue are rising and falling together as a team. Constructive interference. In this case, it's 100% constructive because the red and the blue are perfectly lined up So this total 12 would be the answer we'd get if we added these two together. 7 and 5 get us 12. There is no loss of amplitude. Contrast that with this, which would be partial constructive. So they're kind of lined up, but not quite perfectly. We get an amplitude that's bigger than the individual waves, but it's not equal to the two waves added together. Okay, so if we added these up, 6 and 6 should give us 12, and instead it's only giving us a fraction more than 8. All right, so this is partial constructive interference. Again, it's still constructive because our combined amplitude is bigger than our biggest amplitude. We have another phenomenon known as beats, B-E-A-T-S. And with beats, it's when you have two waves of slightly different frequency. So if you look, the red and the blue waves are not of the same frequency. They start synchronized with constructive interference, but about half a second later, they have reached a state of destructive interference. And when we're back to the 1 second mark, they're back to constructive interference. So it goes constructive, destructive, constructive. And then that pattern repeats itself once every second for this example. Again, this happens when you have two waves of slightly different frequency. So in this case, 7 and 6. Okay, they're only off by a frequency of 1. So the sound intensity will oscillate with a frequency of 1. It will go loud to soft to loud once every second. If we were to combine them and just graph out the total wave, it would look something like this. And you can see how the amplitude goes from very large to nothing and then back to very large again every second. These are called beats, B-E-A-T-S. They're called beats because the sound itself seems to pulsate. So I'm going to play you two sounds that are very similar to each other and then the combined sound. There's frequency 1, frequency 2, and then you hear the pulsing sound when I played frequency 1 and frequency 2 at the exact same time. In this case, they were 256 hertz and 257 hertz. Again, slightly different frequencies. If the frequencies are more than about 7 hertz apart, you will not be able to detect this pulsation of the amplitude. However, we can create what are known as musical relationships, and they usually involve a much bigger gap in frequencies. So in this case, we have 256 and 512. We've already learned these are called octaves. These two frequencies are 1 octave apart. One frequency is double the other. And because of this, you get a repeating pattern. It happens real quick, 256 times every second, so you're not going to detect it as a rising and falling of the amplitude, but you will detect it as a nice musical tone. So here it is. First the 256, then the 512, and then the combined octave. And then combined. Okay, it looks something like this, and you can see it's not a simple sine curve, it's a much richer sound, but it's got a very simple repeating pattern. Big amplitude, big amplitude, small. Again, at such a high frequency that we don't notice it, but we do hear it as a richer sound than just a single frequency. There's other musical intervals that also produce what are nice harmonious sounds. A perfect fifth is when you have two sounds whose frequency are in a ratio of 3 to 2. Frequency 1, frequency 2, combined. Okay, again, a more rich pattern than even the octave was, but a simple repeating pattern. Small, medium, large, and that exact pattern repeats itself continually, and that's pleasing to the ear. A chord usually involves more than just two that have a nice integer ratio to each other. Okay, so again, a much richer pattern, but you can see repetition. You can see those two waves repeating themselves a little bit farther down the line. So these nice chords are a little bit more complex, a little richer sounds, but they still have repeating patterns that the brain experiences in a positive sense. We can contrast that with dissonant sounds where there are not whole number ratios, where they're very confusing patterns, and where it does not have any repetition to it. And those combined sounds are not as pleasing to the ear. So hopefully you understand constructive interference, destructive interference beats, and that musical sounds have nice simple ratios, nice repeating patterns that are more complicated than a sine curve. They're a little richer than a single sound, but they do have a repeating pattern. So anyway, good luck, and if you have any questions, come see me during McCulley 1.